Have you ever wondered if you could turn your trusty DSLR camera into a game controller? Well, today we're going to find out in the next installment of Is It Possible? Hey there, I'm Nikoheart, and today we have a fantastic experiment lined up for you. The concept at hand is taking this handheld camera, or digital single lens reflex camera, or DSLR for short, and adapting it to become a game controller. What you see before you is the world's first look at the Canon 5D Mark III, a camera that released back in 2012, which I've had for over a decade now, giving new life and new purpose as my newest unconventional controller. Now, this project we have been working on since early January 2023, and finally completed version 1 in the late hours of June 16th, 2023. You might be saying to yourself, it looks a little bit janky, Nico. Yes it is. In setting this challenge for myself, I didn't quite realize yet just how much of a challenge it was going to be. And this is only version 1. I plan to continue working on this controller, so consider subscribing below if you'd like to see just how far we can go with this unique, first of a kind controller. Before we get into the nitty gritty of how I made it all happen, shall we show you a little section of it all in action? I also want to give a huge shout out to Lexar for providing us with some fantastic flash memory storage cards for us to use in this project. As during our gameplay and produced content, we'll be uploading the photos taken from the camera after each stream. So with all that, get yourself strapped in and get your popcorn out, because we're about to jump in and show you just how we made it all possible. My initial thoughts going into the project: is there a way that I can capture the inputs from the camera and redirect them to the computer? Conceptually, the idea sounds easy enough, but we had a lot of complexity along the way. Now, I've been using Magic Lantern on my Canon 5D Mark III for the longest time, which is a free software add-on, which runs on either the SD card or the CF card, which stands for Secure Digital or Compact Flash, that adds a host of new features to the Canon EOS cameras that weren't included from the factory by Canon, and it was able to help excel my productivity within filming way back when. Most importantly for us, the Magic Lantern software is open source, meaning we can download the source code and modify it to our own requirements. The Magic Lantern software was built by a process of reverse engineering function and values in the camera's read-only memory, or ROM for short, and then overwriting several of those functions with custom code stored on a flash memory storage card. So my thought was, potentially some modification of Magic Lantern will be able to provide some form of output, maybe even through USB, to essentially log which button is being pressed, and the PC can read those logs, and using software, directly read what is incoming and remap that to keyboard and mouse inputs. I took to Reddit to the Magic Lantern subreddit, which you can find a link to my post in the description below to outline the written concept. Not even a day later, users 99%ADOG and @ML were fantastic in outlining that yes, it could be possible, and here are some componentry that you can use to get started. Great was my initial thought. That is step 1. The next step is the how. Would we even get to such a point of using it? Now, I'll be upfront and honest, I'm not the best at coding myself, so I definitely needed some help on that front. Several individuals actually helped me with this project. Although they've chosen not to be named, I sincerely appreciate their time and energy that they put into this project to make it a reality. So thank you from the bottom of my heart. You lot are truly the best. Within the Reddit post, they were able to direct me to a specific portion within Magic Lantern's code base, which points towards the handle of where common events happen. In this case, most of the onboard controls of Canon DSLRs, aka shutter button, menu buttons, wheels, etc. They then went on to reaffirm my initial thoughts that with the correct software choice and adaptation of code, we'll be able to get that real-time translation of log output to computer functionality that I desire. They suggested to us 2 connectivity choices, so I endeavored to find the best suitable choice for the project. One of those suggestions was just through the USB output on the side of the camera. Initially, this was going to be my primary choice, as we would need a minimal amount of effort, hardware, cables needed to potentially make this happen. There are applications out there that do interface with the camera very nicely via USB for remote and external control, with applications like DSLR controller or QDSLR dashboards doing near to instant functions like focusing the lens, controlling the menus, taking a photo by using PTP, which is the Picture Transfer Protocol, which is most commonly used on Windows or Linux PCs. However, this came at a bit of a drawback. From my personal findings, it seemed like Windows was not great at handling the connected USB, at least from the perspective of the File Explorer window. It would need to be constantly refreshed for any file change in the output log to appear, and if this was the best process for this form of connectivity, it could be potentially exhaustive on my computer. For the most part, I didn't delve too much into it, as I was already a little bit burnt out from prior testing. So USB was not going to be the most adequate solution, so we opted into finding out more information about what UART actually is. UART stands for Universal Asynchronous Receiver Transmitter. Within all Canon cameras, they have a serial port that gives access to a shell or a command line interface that lets you control and receive debug information of the camera. With the aid of Magic Lantern, we can add a specific code to allow it to send extra information through the UART output for a device on the other end to read and translate it for the computer to understand. Now, in the same initial Reddit post, user 99%ADog actually provides a link to the Magic Lantern website, in which there is a photo of how easily accessible the UART output is. Not soon after, user @ML actually gives us a link to DigiKey, which is an electronic components distributor who supply all matter of cables, hardware, testing equipment, automotive controllers, the list goes on, which had the exact cable that we needed to attach to the camera. At this point, I made the choice to commit and explore the route for implementing UART for communication. With this all in mind, we had to figure out just how we were even going to be able to add or modify such code and build the Magic Lantern files to host onto the camera. After doing some searching, I found that Magic Lantern has a public Discord that I was able to join. And I'm going to give some huge shoutouts to a few of the members who steered us in the right direction by helping us get all the necessary components set up and at times clear step-by-step instructions for code. I posted in there what I wrote on Reddit and the concept at hand. And users' names are hard, and Walter Schultz responded with some very helpful insights. They told me that I needed a device that would be capable of reading serial communication from the camera and converting it into readable output on PC that could support 1.8 and 3.3 volts. So I dug around online and stumbled upon this FTDI USB to TTL UART adapter on AliExpress that had all, if not more functionality than I needed. I ordered both the adapter and the cable from DigiKey and a few extras, as if you look at the cables, they are extremely thin, so the possibility of the cables breaking could be high, so it is always good to have a backup or two. Now that was the easy step. The next step was getting this UART cable to connect to the adapter. Now this is where my friend Popeter came to the rescue. Now it has been years since I've last done any form of soldering work. I mean, we're talking about like 8-9 years ago when I was back in university. So I don't really have any soldering equipment at hand. So he came all the way down here with a nice little portable kit to solder the cables together. And here's a little montage of the process. The aim for what we needed to solder was the UART cable to some breadboard jumper cables, so that we could easily attach the jumper cable end to the UART adapter's pin outputs. Now, Popeter did a fantastic job, so huge shoutouts to him for coming all the way down to help with the initial phase of the project. After the cable was soldered, we wanted to make sure that we were able to receive that serial communication from the UART port to the camera. So we loaded up PuTTY, a free and open source terminal emulator, serial console, and file network transfer application. We needed to find what port the UART adapter was on when we tested on my laptop initially, so we went into the device manager to port Common LPT and see that it was on COM port 3. So in PuTTY, we changed the connection type to serial line of COM3, a baud speed rate of 115,200, which is what the Canon camera's output at, and opened a new session. Once in the terminal, all we had to do was turn the camera off and on, and we were greeted by a ton of fast-moving debug information on the terminal, which means that we had successfully achieved UART connectivity. Now I'm going to give NamesAreHard another huge shout out, who went out of their way to make a custom build of Magic Lantern that would effectively be able to output an individual terminal line into PuTTY of each button pressed. I want to give Lexar yet another thanks for sending over this amazing 512GB extended capacity SD card for us to use in this project. On this card, we can load the contents of the zip file created by NamesAreHard, replacing any existing Magic Lantern files, then insert it back into the camera. This SD card boasts a 160MB per second read speed and a 120MB per second write speed, so being able to take photos alongside doing Magic Lantern operations will be absolutely seamless. You can find more information about the SD card and CF card that Lexar sent in the description below. Once the camera has done an SD CF card verification, which you can see happening in the top left hand corner of the screen as I play around with the multi-controller, each line being outputted in the terminal window is showing camera operation, represented by the word button, and a number assigned to each direction I push it in and returning to its center position. This was huge. We now had a fantastic head start in being able to ensure that most, potentially all onboard controls of the Canon 5D Mark III could be outputted through UART. This is where the next hurdle came in. As I mentioned prior, I'm not that much of a coder, and the language that Magic Lantern uses is C, which is pretty uncommon in most modern computing languages these days. So if I wanted to continue to add code to the base build of Magic Lantern, I'd have to bring some friends who may have a bit of knowledge of the language. Once I'd filled them in on the project, we then consulted NamesAreHard from the Discord to help us set up a test build environment on our ends for which we can make our own builds and therefore start the real coding aspects. The first thing that we needed to do was make a Linux virtual machine. Linux is an open source operating system, or OS for short, that massively differs to the common OSs that we know, which are Microsoft Windows and Apple Mac OS. The core piece of Linux, which is the kernel that handles all the memory management, process management, device drivers and system and security calls, handles a wider range of hardware architectures and various programming languages than those of Windows and Mac, which makes it one of the greatest OSs for coders. Instead of getting a brand new PC in order to run this operating system, we can allocate certain amounts of hardware usage on my current PC to virtualize a digital PC. Now with Linux, there are many different distributions of it that all do their own things and have individual benefits, but the one that we are using specifically for this project is Debian, as that is a common distro that Magic Lantern users are building it with. Now that we have everything set up, we needed to analyze what parts of the Magic Lantern codebase we aim to add or adapt to further get as much functionality from the camera for the purposes of the game controller. The important sections of the Magic Lantern codebase were the main GUI loop and the property handlers. The graphical user interface, essentially what is presented to us on the little screen on the camera. Its main GUI loop is a function that runs continuously, reading internal events from the camera's message queue and passing them out to the relevant handlers. Most commonly, this means reacting to button press events and the like, and the property handlers are designed to monitor specific values in the camera's memory and report on updates to these values. We can use these to check the status of controls that fall outside of the message queue event model. After setting up a base build of Magic Lantern in the virtual machine, we look closely at the code NamesAreHard added to understand how UART prints. In simple terms, they were able to include a previously found memory address /pointer into the codebase, which holds the internal function the camera uses to send signals via the UART. This particular address is held within the stubs.s file, which is used as a lookup for various addresses in the ROM. The camera does its own UART to debug outputs, which you saw earlier on in the video, but nothing more. So now with the new stub address, we can tell Magic Lantern to push more information out which we assign. When referenced throughout the camera, it'll look for the string name of UART_printf as its calling point. In the GUI-common.c of the custom build names are hard made, what they added was essentially a call to the UART_printf, which is external to the GUI-common to print a log of what button is being passed by the handle common events by feature. With this, we can now determine the button number and have an additional prefix to help with remapping purposes. With this now understood code, we can test all onboard controls of the camera to see what outputs into PuTTY, and the results were pretty much everything apart from the wheels, the shoulder buttons, the top 4 display buttons, the lock switch, and the mode wheel. We also had no outputs associated to the lens, which is something else I want to integrate as part of the game control, and the camera's level indicator, which is tied to the gyroscopic control, which we could potentially use as mouse control. The TLD of the end result is we managed to fix some, but not all of the aforementioned list of camera functionality to output. So let's cover the process of what we did to achieve this. Our next step was to look at the props_value.c file of Magic Lantern to see if any of the property handlers or values in the file may point towards any of the missing buttons or camera functions that could be called and written to the UART. We found one that worked for the mode wheel that fell under the prop shooting mode, so we devised a new bit of code. What this property does is it looks for any changes that happens when you turn the mode wheel, and if it detects a memory value change, it will report that new value towards a buffer which the property references, in this case, the shooting_mode integer. We then want to bring this into the GUI.c file, so the best way we can externally call it is with a prop_handler and telling it to look at the prop shooting mode. We need to copy the prop's data from one memory location to another, so we include a memcopy line that reads from the buffer and prints the shooting_mode integer number values. We also added a prefix of M so that we know the difference between button input and the mode wheel. And as you can see from the results here, it outputs perfectly. In the future, we additionally want to stop the camera from actually changing modes and only output the number change. This, however, would take a lot of extra diving into the codebase, and whilst we're still properly learning how all of Magic Lantern works, for now we'll leave that as a version 2 possibility. Next focus was the lens. Now unfortunately, I can only use the focal length adjust wheel or zoom ring on my lens, as my focus ring is sadly broken at the time of recording. However, we were also able to find some information in the props_value.c file again for the lens. The zoom ring is linked to quite a large data structure, including values like lens rotation, lens step, focus position, etc. We decided to focus, pun intended, on the focal length value as the clearest indicator of the ring status and report that to the UART port. We noticed, however, that this value was received continuously about once per second, instead of when changed. To prevent sending excessive outputs, we added a check to ensure updates were only sent through when the value actually changed, which you can see with these lines of code here. Due to the update rate, however, changes to this control may have up to 1 second's latency, so we would need to account for this when choosing what control in-game to assign it to. Third focus was the gyroscopic data of the camera. This is where we arose one of our biggest hurdles. Just like the mode wheel and lens, we were able to find right property handlers that would work with the electronic leveling of the camera. Initially, we could only get it working when you're actually in the electronic level view of the camera by pressing the info button 3 times, as you can see here, and somehow locking the controls so that it only operates in this view. The problem here is that if I was to press the shutter button, it would take it back to the main GUI screen, and as thus, the gyro data over UART would stop. We did manage to find an alternative solution by being able to report the information on demand via the use of the GUI_set rolling pitching level status function and integrated into the main GUI loop, as seen in this screenshot of the code of one of our prior testing builds. Once gyro reporting was enabled, we could capture it via another property handler. Rather than single value outputs this time, we needed to collect roll and pitch values from the sensor. These would report as two separate 8-bit values, which we could combine into 16-bit values, and then output it as one whole line of data. The only problem with this approach is that the gyro data from the camera is outputting at about a 300 millisecond latency, which if you look at this presentation or gameplay footage of me trying to use this to operate the camera in game, it's just not user friendly. And the amount of having to adapt to a situation would add for more mental complexity and just plain annoyance. So after some further research, we decided as an executive decision to add an external component to the camera to help it with relaying more instantaneous gyro data, which I know it's nice to keep everything internal to the camera, but for personal preference, this was a step in the right direction. Our component choice was the Arduino Nano 33 IoT, which IoT stands for Internet of Things, which has a gyroscopic sensor and accelerometer, which we can place at the bottom of the camera. We then added in some quick code into the Arduino, which from the Arduino's proprietary integrated development environment, or IDE for short, can present the accelerometer's serial output. So if you see me turning the camera now, it's reporting near instantaneous logs of the roll pitch changes, which is what we majorly needed for this project. These were the only main things that we could implement for version 1, as the other items mentioned would potentially take a lot of reverse engineering to look for specific memory value changes at an undiscovered address in the ROM that may or may not associate with that camera function, and then producing our own stub memory addresses. We did spend nearly 3 months of looking through the ROM, trying to analyze the ROM with Ghidra, a free and open source reverse engineering tool developed by the National Security Agency of the United States, making lots of testing builds which could log the potential changes, but our results weren't proving much use, and could take many more months to eventually find that one needle in the haystack. However, one funny line in the ROM seems to reference "not my job," which gave us a good chuckle. The last part of our codebase we wanted to implement was a way to lock the buttons, so that if we were to press a button on the camera, it wouldn't actually change any internal functions. So we added a button_locked bool, which will act as a true or false when a state is changed, and wrap specific code relevant to the camera functions to what is logged in conditions throughout the code. As mentioned earlier, we couldn't apply this to everything, but for what we were able to, it still performed as we would have hoped. So with that, we have all the necessary buttons and inputs of the camera logging ready to convert to act as a game controller to the PC. However, we wanted to go just a little bit more fancy. A close friend of mine in the content creation industry who I told about the project gave me an idea. They said, hey, imagine if you were to press the shutter button in a first-person shooter game, and then it could be like maybe a flash on a cable or somewhere in the body, basically some kind of LED inclusion. And this got us thinking, the Arduino could be used to animate some of the LEDs in accordance to the remap we were going to make. So my friends working on the project loved this idea, and they actually went out of their way to go get an LED strip and an ESP8266, which is a low-cost Wi-Fi microchip, and the Adafruit NeoPixel library. The nice thing about the ESP8266 is with it being an Arduino compatible microcontroller, also a Wi-Fi controller, we were able to set up a basic web interface using REST API to wirelessly control the LED strip opacity, color, and trigger its preset animations, using Arduino's IDE and using Auto Hotkey. We were able to trigger the LED strip animations by pressing a button on the keyboard, which was able to turn the strip off and on, turning on zones of the strip, and changing the color of the LEDs. This worked really well. However, when we started to introduce the Arduino Nano 33 IoT, the ESP8266 became redundant, as the Nano was able to adopt the code we had already written quite nicely, in tandem with the accelerometer info being transmitted at the same time. However, instead of using Wi-Fi as the control method, we opted to transmit all the data over USB, which whilst it has its limitations of range which the controller can be addressed at, the benefit would be the ease of setup if taking the camera controller to different locations, and not having to constantly sync up the Wi-Fi, for example. We then looked around a bit more and found an LED ring that we could put onto the lens of the camera, so that visually, you can really see the custom-made animations more than you would say a strip that went down the USB. They then soldered the data and power cables of the LED ring to some cables so that they could then be attached to the pinouts of the Arduino and have better connectivity to send rapid changes and better communicate how it integrates with the Auto Hotkey software. Speaking of Auto Hotkey, this was the primary software we ended up using for not only the LED side of things, but also for the camera to game controller remapping. Auto Hotkey is an application designed to automate inputs based on its own scripting language. It is typically used for macroing functions such as form fillers, auto clickers, and the like. Since its scripting language is quite powerful, we were confident that we would be able to use Auto Hotkey to read the serial port. And with a little bit of research, we were not disappointed. We found the script for reading values from the serial ports and adapted it to our needs. We've linked the script in the description below. Our first step was to be able to modify the RS-232 loop, which is a standard protocol used for serial communication, to be able to maintain two loops, one for the Arduino to control the LEDs and handle the accelerometer data, and the other for the camera's UART, and ensure the data matched the speed and parity of the data received, and that it was collected a line at a time for it to pass through a processing function of the script. Then all we had to do was build a large switch statement to convert the various button events we received from the camera into game inputs. For example, we set the multi-controller to act as WASD inputs on the computer. If you look at this set of code, each of the button numbers we had figured out earlier on while testing all of the inputs on the camera are given a down and up input. So say if I was to press W on B54, it would ensure that WASD are given an up input to ensure the buttons aren't currently being pressed. Then it sends a down input for W as the only button active in that range. We had to add some directives to the script to ensure inputs were passed through quickly and in a mode that would work in-game. The more challenging aspect was converting gyro data into usable mouse movement. Firstly, we couldn't use AHK's own mouse movement operations, as these would rarely be recognized in certain game engines. Instead, we needed to use a custom library to send low-level mouse inputs. We brought the LL mouse library into the fray, which is also linked in the description below. With this in place, we were able to move the mouse within games using AHK. It took a lot of trial and error to feel out the right sensitivity scaling and tick rate for the mouse inputs, with some dead zone in the very center of the roll and pitch to make it as comfortable to the user as possible, at least for myself, and give it the best sensitivity for mouse input in-game. And with that, we have made the world's first camera game controller. 6 months of hard work, research, testing and trialing, hundreds of builds made, but it is done. I'm extremely proud of the end result and I cannot wait to bring it to all forms of my future content creation across all platforms. At the point of launching this video, I'll be live streaming with the camera controller over on twitch.tv/Nikoheart with a first playthrough of Elden Ring. So make sure you follow me over on Twitch and also check out the Nikoheart YouTube channel where we'll be posting regular VOD uploads from the streams. Again, I want to give some final thank yous. Firstly to Lexar for sending us the amazing flash memory storage cards for us to use in this project. Secondly to the Magic Lantern Discord, and to Names Are Hard, and to Walter Schulz. Magic Lantern is constantly looking for developers, so if you have any experience in C coding, hit them up as they are looking to bring the software to more Canon cameras in the future. Also, huge shout outs again to my friends who are helping me code for the camera controller. I could literally have not done this without you, so thank you so much. And thank you so much for watching as well. If you enjoyed it, be sure to like the video and subscribe to the channel so you don't miss out on any future content. As always, let me know in the comments below your thoughts and if you have any ideas for any other forms of controllers that we can cover on this channel. Thank you all so much for watching and we'll see you in the next one. I want to give a huge shout out to our Ko-Fi members for their amazing kindness and continued support for Is It Possible? If you'd like to support the production and the development for future episodes, head over to www.ko-fi.com/Nikoheart.